the law of sines and the law of sines.
Well, Algae 2, this is going to be our very last lesson for the year. And rather than talking more about logarithms or maybe going back to exponentials or possibly doing a review of older topics, what we decided to do here was a little lesson on something that will show up towards the beginning of pre-cal, which is going to be trigonometry. Little observation before we get into all of that stuff. Despite the fact that pre-cal is called pre-cal, which sounds like it leads directly into calculus, it is heavily weighted on topics that show up in geometry. Okay, so a year ago, well, over a year ago, you did some other stuff and you haven't looked at any of that in a year, and now we're going to revisit it within the pre-cal content. All right, in particular, the one that I'm going to be looking at today is trigonometry. All right, trigonometry is the study of the relationship between the side lengths and the angle measures of triangles. Now, we really want to kind of break that down and understand what that means here. The relationship between the side lengths and the angle measures of triangles. See, before you learn trigonometry, the stuff that we tend to do with triangles, you do a lot of this stuff. You do Pythagorean Theorem, which allowed you to know a couple of sides and then find a third side, given that it was a right triangle, and that's a key thing that had to be a right triangle. And you also did the triangle sum, that all the angles in a triangle added up to 180. However, you never did any problems where you took angle measurements and you used those to figure out the side lengths, or vice versa. All right, so the very basics of trigonometry is this acronym that we call Sohcahtoa. Okay, the beginning so stands for the sine is the opposite of the hypotenuse. Make sure I say all these right. We have Sohcahtoa is the cosine, and that's going to be the adjacent over the hypotenuse, and then the tangent is going to be the opposite over the adjacent. That was kind of hard to get through there. Sohcahtoa. Okay, the thing about that, so that builds a relationship between the side lengths and the angles as ratios. And I'm not going to get into a lot of depth with all this stuff. You can go look that up if you want to individually, but today's focus is going to be on the law of sines and cosines. Okay, but there is a restriction to that, which is just right triangles. You could only apply this to right triangles. Now I'm going to show you some other stuff here, which is going to allow you to apply trigonometry to triangles that are not right triangles. It does not mean that Sohcahtoa is not important. It is incredibly important, and you definitely need to know it for physics because it helps you figure out horizontal and vertical components. If you've never heard of any of that, it's not going to make sense. Just take my word for it. You still need to know Sohcahtoa. But we're going to talk about two other things today here. All right, so I'm going to skip past this part here for just a second and then describe like the situation. What I have here is a picture of a triangle that is not a right triangle. So if you're interested in solving for different parts of it, you can't do Pythagorean Theorem, okay? You can't like take two sides and find a third one using Pythagorean Theorem if there's not a right angle there. By the way, that does look like it could be a right angle, but it is not one. Here, I'll take something that's got a 45-degree angle on it and show you that it's not going to fit appropriately in that corner. Okay, so we don't have a right triangle here. So there's two methods that you can use to figure out more parts of triangles. Now, one of the things, let me see if I have it written a little bit further above. I don't know if I wrote it in here, but one of the requirements is that you have to have three parts to a triangle regardless. Okay, so if it was even doing Pythagorean Theorem, you knew the right angle and you knew two sides. Okay, so you always need to know three things here. Okay, now, there's four different cases that we can give you three parts. There's four different cases that we can give you three parts, and when you divide up all those cases, two of them will fit what is called the law of sines, and two of them will fit the law of cosines. Okay, so I'm going to give you an example of a picture that's going to work for the law of sines first. All right, so I just have a picture of a triangle that, by the way, I haven't measured at all. Okay, and I wanted to do it this way so it's really like authentic. What I'm going to do is take one side measurement. Let's say we do this one here, and I'm going to do it in centimeters because it's easier just to choose decimals here. So that looks like it's about 11.8. And again, I promise I have not measured any of these right now, and I wanted to make sure I just did it as authentic as can. Okay, so I'm going to measure one side, and I'm not going to measure the other two. Obviously I could, but I'm not. Next, I'm going to take, I had that right there a second ago. Next, I'm going to take a protractor, which you can have a little laugh at my geometry students because they still don't know how to use them. I don't get it. I hope you know how to use a protractor. Okay, but I mean, maybe that should be a laugh at me that I can't teach how to use a protractor, but I'm not taking the blame for it. It was them. Okay, this, it's kind of hard to see it from my angle because the camera's right above it, but I'm thinking we've got about 34 degrees. I don't think it's at the 35. Okay, so 34 degrees. And I'm going to take one other angle measurement, which is going to be the one at the top. Probably would not have guessed that's what I'm going to do, but it's going to fit what I want a little bit better here. All right, so it goes past 80, about 1, 2, 3 marks. So let's say 83. Okay, this would be one case where you can use what is called the law of sines. Now, let me talk about what this is an equation here. What the equation is, it's actually a proportion. What it says is that if you were to take the sine of an angle measurement and divide it by the side across from it, notice the capital A and the lowercase a. If you take the sine of an angle and divide it by the side across from it, it will be equivalent to taking the sine of another angle divided by the side that's across from it. Okay, now obviously you've got three sides and you've got three angles, so it doesn't really matter which ones you're using. What you want is to create these pairs. Okay, now that means that there's four variables in the equation, right? You've got two angles and you've got two sides. So to do this, you have to have three of them. Okay, so if I'm looking for a capital B, that means that I have little b and then I've got these a's here. All right, if I'm looking for little b, that means that I got capital B and I've got these over here. But no matter how you do this, when you take out one variable, you're always going to have one pair of a letter. Like if I take out one of these, I've got my A's. If I take out one of these, I've got my B's. Okay, so the main rule to using the law of sines is you have to have an angle and a side that are across from each other. And that's why I chose that angle, the 83, and not this one. Now, as a side note here, see if you can follow this. If I took the measurement of this angle, and I knew this one as well, so I got both of these, I really know that one because I could just subtract them from 180. So it really didn't matter which one I measured. It's just more direct if I show you this one. And that might show up in the practice problems as well, that you get what we call an included side between two angles, and then you just do the triangle sum to get the last one. Anyhow, get into some work here. We're going to take the sine of that angle. We're going to divide it by the side across from it. And we can set that equal to the sine of that angle divided by the side across from it, which we don't know, so let's just call that x. I could call it little b, you can do whatever you want, but you put something in there so you've got like not just a dead space. And that's your equation. That's going to solve for this. And here's how really nice this is, because there's two things. You're matching up things that are across from each other, which is really easy. That's not hard. And then once you have this set up, it's actually just quick cross multiplication. You're going to multiply these two things, then divide by the other corner that you've got there. All right, so all of this is done in a calculator. You can do it on a cell phone calculator. You just turn them to the side. You just got to learn to, it's like typing it in backwards when you do it. But here's using a graphing calculator. You do, no matter what type of a calculator you use, you do want to make sure that you're in degrees for this problem. So I'm going to go to my mode, and I'm going to verify that I am on degrees. The other option is radians. In pre-cal, we're going to do more stuff in radians than we will in degrees. But that stuff's not going to make any sense to you today, so it wouldn't be a good idea to choose that. So we're going to do it in degrees, but be aware that that radians is going to be our top dog when we're in pre-cal here. All right, so with that set, I'm going to take 11.8 and I'm going to multiply it by the sine of 34. You don't really have to type multiply because calculator will understand that that's what we're doing. So if you do it with the number and then the trig part, everything works great. If you put the trig part first, you need to multiply and close the parentheses and all that stuff. So it's easier just to put it in that order. Okay, so we get back that number. Okay, that number does not represent that side. And usually it doesn't look anything like it should. But it actually looks kind of close. It's here. So be very careful that you don't finish the problems too fast here. What we're going to do next is divide by the sine of 83, which happens to be a very small number. And you'll learn why in pre-cal, why it's a very small number. But it is going to change that appropriately there. Okay, so I'm going to divide my last answer by the sine of 83. And it's not going to change as much, okay? Yeah, I mean, when you look at these side by side, they look like they're almost identical, but make sure that you do divide by that. In some other problems, it's going to be a little bit more dramatic when we do that stuff here. So again, I'm doing the problem very authentic, so I didn't really like plan for something to be that close, but you do need to finish your cross multiplication. You need to multiply. You do also have to divide. So there's two steps that are involved here. Okay, I believe the answer to be about 6.6 to 6.7. What did it say? It'll round up to 6.65. Okay, now again, you're not going to see too much of a difference in both of these answers here, but the last one is the right one after you divide it. And then just to verify, I'm going to put my ruler on top of that, try and get it lined up. Again, hard to do with the camera right above it, but if you look really close here, it looks like it's just reaching out to 6.7. Now, there's going to be a little bit of variance in how you measure things, because you can't measure beyond the tenths place when you measure. So these might not have been, like that might not have been exactly 11/8. But I mean, you look at that, you got to trust what we're doing here. Some good work. All right. All right, so the next logical thing, I'm not going to make you go through this process. I'll measure it because you might want to try it out on your own, but I'll give you a little bit of numbers here. I'm kind of just thinking off the cuff at the moment. All right, we have the angles 34 and 83. So if I add those up, I get 117. I'll subtract that from 180 and get 63 degrees. Okay, so this is 63. Okay, and we don't know that side. So independently, try this out. Do the sine of 83 or 11.8 and set that equal to the sine of 63 divided by whatever that side is. So I'll give it a new variable. I'll call it y. All right, now the answer in the end, I'll let you run the calculation and see that you get that. And I'm going to trust that this all works. But the measurement is what you would see there. Hopefully I got it lined up correctly. So I'm looking at about 10.5 and see if all that works out to give you 10.5. Right. At the beginning, I had mentioned that for both of the laws, the law of sines and the law of cosines, there's two different versions of problems that you can do. At least I think that I mentioned that. If I didn't, then I am right now. There's two cases for law of sines. There's two cases for law of cosines. Okay, so let me jot down law of sines one more time. So the case that we did in example number 1 was having us find a side. You were looking for a side length. The other case that we could be doing for the law of sines is looking for one of the angles. Now, the fundamental thing here is that if you are going to use that law and not the law of cosines, you do have to have an angle that would be across from a side. Okay, so what we're going to do is we're going to sketch this up and we're going to see that that is apparent, that you do have that pair. But we're going to be solving for an angle instead. And it changes the math by one step at the end. Just at the very end, there's one extra step that would go on there. Okay, let's see. I'm not going to draw this to scale because it'll take too long to do it. But we do have an obtuse angle of 126 degrees, and we've got two side lengths here. We have a 12 and a 7. Okay, so in my sketch, I'm going to put the obtuse angle up at the top. I don't know, like, if this is going to look close at all. But one of the things about trigonometry, in fact, I kind of drew that to look isosceles, and it's probably not one, so I'll just, that might be a bad idea too, but I'll extend out one of the sides. But look, the thing about this is it's all associations of where things are. And we're going to see that in law of cosines too. As long as you can get things organized by what they're across from, the math is going to work out. You just got to remind yourself that your picture might not look the way that it's supposed to. Okay, so I'm going to let this be angle S as the 126. So I at least made an obtuse angle there. Let's see how close I actually was, because I have no idea. But I'm curious here. I'm curious. Look at that. Not even close. 126 is going to be, it's going to be over there. Okay, so the picture, it's garbage. Know that from the beginning, it's garbage. All right, we got RST. You need to label everything. Okay, an angle S here is 126 degrees. Little s is 12. That means that this is 12. See the organization. And the fact that these are across from each other is going to tell us that we should be using the law of sines. I'm so confident with that, I'm going to go ahead and start writing up this part. Now, I don't know what the other side looks like yet, except there's a fraction bar. Okay, so other information we've got that little t is 7. So that's going to be over here, all the way across from that angle, that arrow. All right, so the only thing that we could solve for, and this is interesting, the only thing that we can solve for here is angle t, at least directly. Okay, so we're going to have the sine of t. So capital T is hanging out up here on the top with the sine, and then the 7's on the bottom. Now, that's not to say that you can't solve for other things. Like you can't figure out what angle R is. Sure you can, after you figure out what T is. Once you figure out angle T, then you can subtract from 180 and you're good. Okay, and then once you've got that angle, you could do another law of sines if you want to figure out what this side is. So you can actually get everything you need given any three pieces, as long as you have a side length. You got to have at least one side length, otherwise you don't know what size the thing is. But if you got three pieces, you can solve for everything. It just might not be a direct solving. All right, so here's the math. Again, it's cross multiplication. You are going to multiply the diagonal that you got. So, again, I'm not sure on the lighting here, so I know that it works well with my calculators on this side. All right, so I've got 7 multiplied by sine 126. Also thinking at the moment here that if you don't have your calculator set to degrees and you're in radians, your answers are going to look really wacky. You're going to get like negative numbers and really tiny numbers, and like just outrageous stuff is going to be happening. So if you're doing any math and you're really thinking about numbers you're creating and they don't seem to make any sense, check your setting in your calculator. Okay, now this calculation isn't supposed to mean anything to us in the picture. It's just multiplication there. So I want to be careful that like in the middle of a problem, they might not make sense. We're talking about the end. Okay, so we multiply those two together and we get that number. We then have to divide by the 12 and we get that number. Okay, and I think this is what I was more imagining would happen in example number 1. You get an answer that does not look like what it should be. That angle right there is not 0.47 degrees. That's not true. Okay, what that number represents is actually the sine of t. The sine of t is equal to 0.4719. You need at least 4 decimals when you do trig. If you're just taking the trig of something, yeah, you need at least 4. That's the rule. Okay, so this is the sine of t that gives us that angle. Now, I don't know if you remember this from geometry. Like I said, this stuff's important because you don't see this in Algebra 2 at all. This is all the way back to geometry. What we have to do is take the arc sine. The inverse sine is what it's also called, but I was taught arc sine by Mr. Spiller, so I still remember it that way. You press second sine. That should be true for pretty much every calculator that you have. We want to take that answer in there. Best method is to recall the last answer. That's pressing second negative, which is also true on the inspires. Press enter, and now we get a number that that makes more sense. For a moment, I thought it didn't because it would have been a side length, but we're not looking for a side length. We're looking for an angle. 28, for degrees, I usually go 1 decimal, so 28.2 degrees is what we got. And that, since everything's in green here, I'll draw a little red arrow. That is angle T. Okay, so that would be the other version of using the law of sines, where you're finding an angle. Everything looks pretty much the same. You cross multiply, like multiply the diagonal. You divide by your other corner, but then you do an arc sine. You got to get rid of that sine to get back to the angle measurement there. And as mentioned before, if your problem begins a certain way, you can only get one answer. But now that I have that answer, I could add the 126, subtract to get 180, okay? Then I could use that angle along with this pair to solve for that side, and it looks exactly like example number 1 when we did it. Oh, so law of cosines. What do you do if you don't have a pair across from each other? If you can't completely set up one of these, what do we do in that case? Law of cosines. You can't use the law of sines all the time. Man, it'd be awesome if you could, because it's just simple cross products. You match things up, and after you do, literally, probably, if I over exaggerate here, maybe like 10 problems, then you're an expert at it. It doesn't take you long to figure out what's happening with that stuff. Okay, but there's these two cases. There's only 2 of them. There's 2 cases where you cannot use the law of sines. In the past, I used to describe it as if you don't have an angle and a side across from each other, because you're always looking to use law of sines first. If you don't have that, then use law of cosines. But then, like, as I taught this a little bit more, I kind of thought, you know what, I should probably just describe the 2 situations, like have a description of what they look like. So description number 1, you have all 3 sides. And it's such an easy way to explain this, right? You have all 3 sides here. That means you don't have any angles, which means you don't have any pairs. You just have all 3 sides on there. But look, given all 3 sides, you can figure out what any of the angles are that you want. And you're going to be using this guy here, which is called the law of cosines. I didn't read the top part up here, but provided that you know all 3 side lengths of a triangle, so that's our case right now. Or if you're given 2 sides and the included angle. So that's going to be the next part, and I'll elaborate more on that when we get there. So we're looking at the first case, which is you have all 3 side lengths. Okay. All right, so this is the law of cosines. I'm not going to get into the depths of like how either the formulas are created. When we actually cover this in pre-cal, sure. We're going to take the time, we're going to break it down. This one's a bit tedious to get through and to show what it is, but we'll talk about it later. One thing that I do want to point out is it looks a lot like Pythagorean Theorem. The letters are moved around for conveniency here, right? And C doesn't represent a hypotenuse because we don't have a hypotenuse here. It just represents a side. But we have an a squared, which is equal to a b squared plus a c squared. So there's a lot of similarity between Pythagorean Theorem. And it is okay to think of it that way. In a way, the law of cosines is using Pythagorean Theorem when you don't have a right triangle, which is wrong. It's wrong, you're not allowed to do that. But this whole chunk here at the end, you can look at as being the adjustment. We are incorrectly using Pythagorean Theorem. We're using it in a situation you shouldn't. But if you adjust by this amount, you will get it to work. So you can think of it that way if you want. And I hope that might break down some of the parts on this. All right, so here's what we got. Little a, little b, and little c. These are all side lengths because they're lowercase letters. All right, and little b, little c, they're side lengths that are there, and capital A is going to be an angle. So we've got 4 things involved like we saw in the last formula. But in this case, you're going to have the 3 sides and you're going to have 1 angle. And look at that. Little a and capital A, 2 things that are across from each other. But you can't do that, right? Because if you're going to have 2 things that are across from each other, it has to be law of sines. But here's the interesting thing in this problem, is that you're never going to know both of those numbers. One of these 2 will always be the variable. B and C will be numbers that you do have. It's going to be the A's, one of those 2 that's going to be missing. Okay, so in our case, we've got all the lowercase letters. We've got all the sides. So we're going to be looking for capital A here. What's the example actually say? It says solve the triangle. Okay, so when it says solve all the triangle, that means to find all missing parts. Okay, what I'll probably do is take you through just one of them because I know this video is already going to be super long. I'm basically doing 2 lessons in one. Okay, so I'm going to show you how to do one, but then I'll just describe how you change it up for the others. And look, you're old enough. You can figure out what's going on here and then match up and try the other ones if you want. All right, so we randomly choose an angle to solve for. And let's do this one. It's called theta, by the way. That little symbol there is called theta. That one is alpha and that's beta. This one's called theta. Okay, so if we're looking for theta, that is going to represent capital A. The angle's got to be somewhere in the equation, so it's capital A. So all these letters are arbitrary. They're just generally to fit. You make them work. Okay, so that's going to be capital A. And really important about that means that 10 is little a. Okay, so we're going to end up, from my template here, we're going to get 10 squared is equal to, B and C are going to be the 5 and the 12. They're the other sides. And it doesn't really matter which one is which. Okay, because they do the exact same thing in the equation. Let me write this before I screw it all up. Okay, they do the same thing in the equation. They both get squared and added together, and they both get multiplied, and then all the subtracting business. So they do the exact same rule, so it doesn't matter which one's which. It really does not. What's important, sort of like law of sines, is to figure out where that pair is. If you're looking for an angle, little a, the one that's on the other side, better be the side that's across from it, and then everything else just goes where it goes. All right, now, I'm going to try not to elaborate too much on this part here. Here's the big thing that you don't do. Do not do this. We're gonna be mad at you for a while if you see you do this. Because I'm putting in the video, by the way. Do not multiply and add and do all of this stuff. Like try and simplify all of that and then divide it into that side so that you can take an arc cosine. Don't do it. The cosine is being multiplied by all this stuff, and then these are things that are being added on. That's totally different operations. Now, if that throws you off a little bit, the way that I'm actually going to do the problem is so simple anyway. See, the cool thing about this equation, I don't know if they intended to do it this way or not. What's cool about it is you can literally just move down the line until you get your answer. Here's what it looks like. You take your 10 squared, which of course is 100. You subtract the 5 squared. Since it's being added onto all this stuff, you just subtract it. Then you subtract the 12 squared. Okay, so that's gone, and that's gone, which gets you just down to this part here. Then these are all things that multiply to the cosine. So we divide by -2. You divide by 5. You divide by 12. Look at that. We just chip away. Gone, 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 gone. To the point that you're down to just a cosine. And to get rid of the cosine, you can do the arc cosine or inverse cosine. And that's it. You can do this every single problem. Just move down the line. It's always going to be minus, minus, divide by -2, divide, divide, arc cosine. For any problem that you're using law of cosines for with the intentions of finding an angle. All right, so we just type it up and do them as individual pieces. Don't try and be too cool about it and too fast. Okay, now some things you can just square on your own if you know them. So take 100, I'm gonna minus 5 squared. That's actually just 25, so take away 25. Subtracting 144, yep. We're gonna get a negative number here. Yeah, -69. Okay, but look, you're gonna, and don't worry about the negatives because sometimes even at the very end with the cosine, it takes care of itself on that one. All right, but leave it in there. So we're gonna divide now by -2, which should get you to 34.5. So it's back positive, but again, that's not always gonna happen here. Sometimes it's still negative. We'll divide by 5. We'll then divide by 12. And at this point right here, okay, you're always going to get a value that is less than 1 or less than -1. It has to be a decimal number that doesn't have any whole part to it, but it could be positive or negative. If that doesn't happen, then something is wrong with the numbers. Maybe you use the same value twice when you shouldn't have, sort of thing. But whenever you get down to your trig part here, your arc cosine, it better be a number less, let's say between -1 and 1, so a decimal form number. All right, so I'm going to press second cosine. Recall that last answer. Could have typed it in, but I just like that method. And we get that, which I want to call it 55, but let's just call it 54.9. So theta is 54.9 degrees. I don't like to round values off to whole numbers unless I'm instructed to, because if you call it 55, then it sounds like it was exactly 55. But this communicates to us that there was probably some rounding that was happening there. All right, for the rest of these, you got some options now. What I would have you do, I wish I knew the answers to these so that you do. I think that this one's around like 109, because I use this problem every year I teach it. I think it's around like 109 degrees. But what you could do is you could repeat this process like in all the arrangements. Let the 12 be over here with the 5 and the 10s, and that solves for alpha. Then do the same thing with the 10, and at the end of it, if you add all your angles together, they should add up to 180, and that's a way to test that if you've done this right. But some other things that are kind of cool here, because I now have theta, and I got the 10, I actually now have a complete pair that's across from each other, which means if I wanted to, I could now do some law of sines. I could do the law of sines to figure out the other angles. Usually what I do is if I start this way with cosines, I just do the next part in cosines because I've already got the rhythm to the problem. But you do have a lot of choices. You can try something different if you want. All right, so the next example is going to be having two sides and an included angle with that one. All right. All right, example number 4. This is going to be our second example for the law of cosines. It's also going to be our last example for the notes, which I'm sure have gone on very, very long here. All right, so this picture is the same one that I have from example number 1. Odd thing about it, I was adding in the numbers, just taking the measurements again independently of what I had done beforehand, because I wanted to make sure that it did copy to be the same size here. All right, and I believe when you see this on the camera, because I'm looking at my iPad to do this part here, it appears to give you a base of 11.8. But if I'm directly over this with a ruler, I'm actually getting 12 centimeters for the base. So I don't know if there's any inconsistency in what you see, but if there is, that's what's happening with this. Hopefully it just looks like an 11.8, so I'm going to keep that number when I do the math. Anyway, enough of that. The last example that we have, you have two sides and you have what is called an included angle. It's an angle that sits between the two sides. Now, law of sines, you can't use that one because the only way you can use the law of sines is if you have an angle and the side that's across from it. Nothing over here, right? It doesn't match up. And the other two angles we don't know, so those don't match the sides that are across from. So you can't use it. Okay, so one case for law of cosines was given all the sides. But the other case is going to be you do get an angle and you do get two sides, but they don't end up laid out in a way that law of sines would work. So we do cosines for this. All right, looking for a spot to write all this. Okay, the law of cosines looks like this. That would be the general template for it. The place that you begin, so once you've identified that it is going to be a law of cosines, you really want to look at the A's, the little a and the big A, because these have to be the two that are across from each other. Okay, in our last problem, you got to choose capital A to be anything you want, well, any variable that you're solving for by choosing any side to be little a. In this case, capital A has to be the 63, because that's the only angle that's involved in the problem. So that's going to be A, capital A. Little a is going to be over here across from it. Then B and C are those impartial numbers that are just kind of there, that are B or C. They don't matter which ones are which. Okay, so here's our setup. We get A squared, because we don't know little a, is going to be equal to 6.7 squared minus, nope, plus, got ahead of myself there, plus 11.8 squared minus 2 times 6.7 times 11.8 cosine 63. Okay, now I'm going to pause here for just a moment. And I know it's been a long set of notes here, but I want you to try and see this on your own. Take a look at this equation and think about how you are going to solve for little a. All right, what I hope dawns on you here is that your variable is pretty much isolated from everything else. It is not embedded into everything else. Now I say pretty much isolated because it's got the squared on there, but it is not embedded with all the other numbers. All of this stuff over here, the entire right side of the equation are all numbers, which means you can just evaluate them all at one time. And literally all at one time. If you don't have a fancy calculator, well, this is one of those moments where it really does sort of stink for you here, because this is great. And it actually takes a lot of effort to explain like which pieces you have to do first and second if you're going to do it as like small parts. So if you have a graphing calculator, this is a great moment for one. All right, let's double check everything's typed in here because I don't want to, it's a big one, right? Don't want to mess it up. Okay, so you got the 6.7 squared. We're going to be adding 11.8 squared. We're going to minus 2, 6.7, 11.8. At the end, we got cosine 63 and closing parentheses for the sake of doing it. We press enter and you get a dat number, which is definitely not going to be the length of A here, right? That's 11 and that's 6. You can't have a length of 112, but there is that little squared that's in it. So if we square root that last answer, and I always recall the last answer to pull all those decimals in there, we now get a number that makes sense, which is about 10.6. All right, and there we are. I know I did that measurement for the same picture earlier, and I think we said there was going to be around 10.5, give or take 1. So that sounds pretty darn good for that one. All right, now if you were asked to solve for the other things, which would have been the other angles that are in the picture, because sometimes we ask you to just solve the triangle. Like solve the triangle means all things. It's already on the page, I don't need to write it. Now that you do have that pair, what you could do is a law of sines to get another angle, and then you could do your triangle sum to conclude this. Or because you have all three of the sides, you could do law of cosines like we did in example 3 to get another angle. It's all up to you. You decide whichever one you want to do. All right, that was a long video there. Usually this is taught in like 2 different days and all, but we're going to do it all in one, and it's only going to have 1 set of exercises as well, so you're welcome. And with that, this is the conclusion to Algae 2 2019-2020. Finish your work, get it all submitted, because I won't do any more videos like this for you. Have a great summer. Do a little bit of thinking, do some exercise, and we will see you in the fall.